Welcome to the Explainer. Have you ever looked at a beautifully complex map and felt like you were, staring at some kind of alien language? Well, today we are officially decoding the Earth. We're going to master the art and science of map reading together, basically translating all those mysterious lines, numbers, and symbols into a crystal clear picture of the physical world around us.
Okay, let's dive into this. Here's our roadmap for today's Explainer. We'll be covering from globes to maps, the elements of a map, exploring topographical maps, eastings and northings, and finally, mastering grid references. Let's get started.
But before we get to the granular details of navigation, we actually have to start with a massive, very literal problem. How exactly do you flatten a giant three-dimensional spherical planet onto a flat piece of paper without losing your way? I mean, a globe is incredibly accurate for showing the Earth's true shape and the relative sizes of oceans and continents, right? But it's totally impractical if you want to find a specific street, a local post office, or a hiking trail. You simply cannot fit that kind of day-to-day detail onto a sphere that just sits on your desk.
So, let's jump right into Section 1, from globes to maps, the 3D to 2D transition. The solution to our flattened Earth problem actually has a name, and it's cartography. It's officially defined as the art and science of mapping three-dimensional features and geographical phenomena on a uniform, flat surface. And notice that I say both art and science. It requires really rigorous scientific and mathematical precision to draw earthly features accurately to scale, but it also takes immense artistic design to ensure that all that dense information is actually readable, intuitive, and, well, useful for human eyes. And this perfectly illustrates what cartography allows us to do. Take two different maps of India. A physical map highlights the natural, physical relief. The mountains, the green valleys, and the flowing rivers, everything crafted by nature over millions of years. But then, a political map of the exact same landmass completely strips away that physical terrain to show us human-made political boundaries, states, and cities. Both are perfectly accurate, flat representations of a 3D space, but they serve entirely different purposes based on the specific story the cartographer actually needs to tell the reader.
Moving on to Section 2, Elements of a Map, the Cartographic Alphabet.
Every map you will ever encounter is built on a foundation of 6 basic elements. You can really think of this as the alphabet of cartography. You've got the title, which tells you precisely what you're looking at. The scale, which translates map distance to actual real-world ground distance. Direction, which is conventionally aligned with north at the very top. Then there's the grid system, a network of intersecting lines used to pinpoint locations. You also have conventional signs or symbols, acting as a quick visual shorthand for physical objects. And finally, the key or legend, which is the crucial tool that unlocks the exact meaning of all those symbols. Working together, these 6 elements give immediate context and scale to what would otherwise just be random shapes on a piece of paper.
A super vital part of that context is the map scale, and cartographers divide maps into 2 main categories, large scale and small scale. Now, definitely pay attention here, because this can feel a little counterintuitive. Large-scale maps, like topographical or property-based cadastral maps, actually show a relatively small geographic area, but they display a massive amount of incredible detail, down to individual properties, tiny buildings, and even small streams. Small-scale maps, on the other hand, think of the ones you'd find in a classroom wall atlas, show a really large area, like an entire continent, but with a distinctly small amount of generalized detail. And for real-world practical navigation, whether you're an urban planner, a military strategist, or literally just going for a hike, we absolutely need that high level of granular detail.
Which brings us to Section 3, Topographical Maps, zooming in for detail.
To truly appreciate these highly detailed maps, it really helps to just look at the word itself. Topography comes directly from 2 ancient Greek words, topos, meaning a place, and grapho, meaning to draw or depict. So when you look at a topographical sheet, you are quite literally looking at a magnificent attempt to draw a place in detail, capturing the exact, undulating surface of the Earth exactly as it exists right now.
These highly detailed topo sheets, which are sometimes also called ordnance survey maps depending on where you are just incredible because they seamlessly combine the forces of nature and human civilization onto a single page. And they do this by simultaneously displaying 2 broad types of features. First up, physical features. These are your natural elements like valleys, peaks, and plateaus, usually shown using contour lines that connect areas of the exact same elevation above sea level. Second, you have cultural or man-made features. This includes roads, railways, bridges, and individual buildings, all represented by those universally recognized conventional symbols we talked about a minute ago. But here's the kicker. All those beautiful, intricate details are completely useless if we can't communicate to someone else exactly where they're located on the page.
That takes us right into Section 4, Eastings and Northings, the coordinate grid.
To find an exact location, maps use a really rigid coordinate grid system made of intersecting lines. The vertical lines that run from north to south are called eastings. Why? Well, because their numerical values increase as you move eastward across the map. On the flip side, the horizontal lines that run east to west are called northings, because their numerical values increase as you move northward up the map. So the crucial point here is this golden rule of navigation. When reading a map, you must always read the eastings first and the northings second. A really classic way to remember this is the old saying, you have to walk along the corridor before you can walk up the stairs.
Let's visualize how this all builds together. The vertical easting lines and horizontal northing lines intersect at perfect right angles, forming a series of really neat squares across the map. And the numbering fundamentally works like this. The origin point of the grid system starts way down in the southwest corner. As you move right, or east, the east two numbers go up, 31, 32, 33, 34. As you move up, or north, the northing numbers go up, 8, 9, 10. These precise intersecting lines form our entire coordinate grid.
And now for Section 5, Grid References, Mastering Navigation.
With that coordinate grid firmly locked in our minds, we've actually reached the climax of our explainer today. It's time to take all this theory and turn it into a highly practical, real-world skill. We're going to start by finding a general location using what cartographers call a four-figure grid reference. Say our goal right now is to locate the settlement of Hipatpur. A four-figure grid reference will allow us to identify the exact 1 kilometer square where this settlement is located. Let's break down exactly how to do it.
Here is the foolproof step-by-step process. First, you find your target object, in this case, the settlement of Hipatpur. Then, identify the vertical easting line immediately to the left of the object. Make a mental note of that specific number. Second, identify the horizontal northing line just below the object. Note that number too. Third, combine them. Just make sure to remember our golden rule. Walk along the corridor, then up the stairs. Eastings first, northings second. Doing this gives you the precise 1 kilometer square holding your target.
And following those simple steps gives us our coordinate, 4385. Let's verify it. The easting line immediately to the left of Hipatpur is 43, and the northing line just below it is 85. By combining them, eastings first, remember, we get 4385. With just 4 simple digits, you've successfully isolated a single kilometer of land on a vast, intricate map.
But cartographers definitely didn't stop there. I mean, a 1 kilometer square is fantastic for finding a whole village. But what if you need to find something way smaller, like a specific temple or a water tank? If you look closely at the settlement of Kedah, there's a tiny red square representing a temple to the northeast of the town. To pinpoint that exact spot, we have to upgrade from a 4-figure reference to a 6-figure grid reference. This is magically going to narrow our search from a massive 1 kilometer square down to a highly specific 100-meter square.
To generate those 2 extra digits, we actually have to use our imagination a little bit. First, you take that 1 kilometer square we just learned how to find and mentally divide it into 10 equal tiny parts vertically and 10 equal parts horizontally. Next, you determine the 3rd figure of your final coordinate by estimating exactly how many tenths across the easting line the object sits. Finally, you determine the 6th figure by estimating how many tenths up the northing line the object sits. It definitely requires a keen eye and a bit of practice, but the precision you get is just incredible.
For that specific temple near Kedah, the magic number is 265902. Let's see exactly why. The main easting line to the temple's left is 26. Mentally dividing the square, the temple sits exactly halfway, or 5/10 across the grid, giving us 265 for the first half of the reference. The main northing line below it is 90. Mentally dividing the square vertically, it sits roughly 2/10 up from that line, giving us 902. Merge them together, eastings first, northing second, and you get the precise code, 265902. I really want to emphasize why understanding this specific concept matters so much. A 6-figure grid reference gives you the ultimate superpower to pinpoint a place on a paper map accurately to the nearest 100 meters. Completely without batteries, without a cell signal, and without a satellite connection, this brilliant analog technique gives absolutely anyone the power to locate post offices, strategic bridges, or safe havens in the real world with astonishing and honestly sometimes life-saving accuracy.
And the truly amazing thing is how perfectly scalable this entire analog system is. These local, highly detailed topo sheets don't just exist in a vacuum. They fit together like perfectly cut puzzle pieces into massive, countrywide indexing systems.
For instance, in the Survey of India's Open Series map, the entire nation is divided into an overarching grid. Each larger square is systematically numbered and lettered. This means you could be handed a tiny, isolated slice of topography and, just by using these references, instantly know exactly where it belongs in the grand scheme of the entire subcontinent.
Which leaves us with a final, fascinating thought to ponder. Today, we've decoded the art and science of traditional map reading, successfully navigating from a massive globe all the way down to a 100-meter square using eastings and northings. But how does the foundational language of these brilliant analog grids translate to the invisible GPS satellite tech hidden inside your phone today? The digital tools have certainly evolved, but the underlying geometry of finding our exact place in the world remains remarkably beautifully the same. Thanks for getting focused and exploring this with us, and I will catch you in the next explainer.